All right, we're now in section 3, which is where we start getting into the math behind all the gases. So we've got a few sections under our belt. We're ready to go with how gases behave. So now we can start applying mathematical representations to them. And starting off with the ideal gas law. So the ideal gas law zeroes in on the 4 behaviors that can really affect how a gas actually behaves. And those 4 physical variables are pressure, volume, temperature, and the number of moles. So think about it. Those are the 4 things that are really going to dictate the behavior of a gas. And so collectively, these variables can be expressed using the ideal gas law, which is PV equals nRT. A lot of times, you'll hear people say PivNert, and you're like, what the heck are they talking about? They'll say, use PivNert, and you're like, okay, they're referring to the ideal gas law. When we're going through and we're taking a look at all the different variables that are in this gas law, we've got P, which stands for pressure, V, which stands for volume, N, which is going to be your number of moles, and then T, which is going to be your temperature. But then there's this R, and the R is the gas constant. Because it's a constant, it's an actual number. You'll never have to solve for R. You'll always just have it. It's a number. The gas constant is 0.08206. And then notice these funky units here. It's atmosphere liter over mole Kelvin. So this value is on the back of your periodic table. You don't have to memorize it. But because of these specific units that is in the gas constant, we need to make sure that we have the units correct for every other variable. So pressure has to be in atmospheres, volume has to be in liters, moles has to be in moles, obviously, and then temperature has to be in Kelvin. In all gas laws, it has to be Kelvin. And the reason why is because when you put all those in the correct units, they'll cancel out. So one of the big things to keep in mind when we're going through and doing these problems is we need to make sure that we do conversions first to make sure everything is in the unit it needs to be. All right, now why is it called the ideal gas law? Well, because it works for ideal gases. What is an ideal gas? An ideal gas is one in which a sample of the gas's behavior is predicted by the ideal gas law equation. In other words, if we can accurately predict the properties of a gas using the ideal gas law, then the gas itself is behaving like an ideal gas. I know that kind of sounds like a Webster's dictionary definition. You're like, that doesn't really help me. But let's say we were looking at a sample of a gas in the lab, okay? And we used the ideal gas law to predict some behaviors that it might do, right? And if the gas actually, was in line with those predictions, then we could accurately say, yeah, the gas that we're analyzing is behaving like an ideal gas. Most of the time, the difference between an ideal gas and a real gas, like, reality, is very small. In fact, we'd say it's negligible. So all that to say, when we're in the lab, provided that we're not dealing with any extreme situations, all of the gases we deal with are essentially ideal gases. A real gas is only going to deviate from the ideal gas law under conditions of extremely low temperatures and or extremely high pressures. So once again, the ideal gas law will deviate from the gas behavior if it's extremely low temperatures and or extremely high pressures. So keep that in mind. This down here is nothing you need to memorize. I put this here just to show you advanced levels of chemistry. How do we account for a gas when it's under those extreme conditions? You can see we make some slight variations to the ideal gas law. There's your pressure, okay, but here's obviously some variations. There's your volume with some variations. We're still familiar with the nRT part, but you can see we have to do some corrective measures for pressure and volume. Like I said, you don't need to know that. I'm just showing you that there's some extra steps you'd have to do if we were working with some conditions that were very extreme. Nevertheless, all that to say, let's get started, right? Let's start unpacking the ideal gas law. So we're going to start off with a really simple example just to get our feet wet. What is the volume of 5.12 moles of an ideal gas at 32.0 degrees Celsius and 749.5 torr? Okay, so first thing I would tell you to do is analyze the problem. And what that means is let's write all of this information in variable form. So it says, what is the volume? So V equals question mark of 5.12 moles. Well, moles is the n variable. So it's 5.12 moles. The temperature here, so temperature is T, and that's 32.0 degrees Celsius. And then the pressure is P, and we're told it's 749.5 torr. Okay, so after I analyze the problem, I can see, oh, we're looking at an ideal gas law equation. Right now, it may seem obvious that we're dealing with the ideal gas law because that's the section we're in, but on an exam, you may not know because we're going to go over some other gas laws later on. So it's always good to analyze the problem. Write down what it's giving you so that way you have a clear idea of what it is that we're looking for. So we're going to be using Pivnert, good old Pivnert. But what I'm going to do is I'm actually going to rewrite this equation to solve for V. So I'm going to divide both sides by P. And so we end up getting a little bit of a different version of the ideal gas law. Volume is equal to nRT divided by P. Now, before I just start plugging things in there, we need to make sure everything's in the correct unit. So N is mole, so that's good. Temperature needs to be converted, right? So we're going to add 273.15 to temperature. Okay. Now, remember, when you add, you always have to show your answer with the lowest number of decimal places. So even though when I just simply add, I end up getting 305.15. But notice there's 1 decimal place versus 2 decimal places. So when I record my answer here, it needs to have the lowest decimal places, which is 1. So really, it should be recorded as not 305.15, but it should be recorded as 305.2. Okay, and then that's Kelvin. So that's how we convert the temperature, and then to convert pressure, remember it has to be in units of atmospheres. So we're going to go from torr to atmospheres, and for every 1 atmosphere there are 760 torr. So we just divide by 760. So 749.5 divided by 760. Remember that 760 and 1 atmosphere are exact, so we're still going to keep our 4 sig figs. So my answer is 0.9862 ATM. All right, so now I've got my pressure, my temperature, and my moles all in the correct units. So now I'm going to go ahead and start plugging things in. Volume is equal to my number of moles, which is 5.12, times the gas constant, which is 0.08206 atm liter over mole Kelvin, times the temperature, which is 305.2 Kelvin, and then all divided by the pressure, which we converted was 0.9862 atm. Now before I calculate, just want to quickly show you, the moles are going to cancel, the Kelvin are going to cancel, the atmospheres are going to cancel, and so our unit of volume is going to be left over in liters. All right, so let's calculate this. Okay, and when I get my answer, it looks like my lowest number of significant figures out of all 4 of these values given is 3 sig figs, because the number of moles. So I'm going to round my answer. It's 130. Okay, I'm just writing 0.023. I'm just writing down what the calculator gives me. Blah blah blah. How do you turn this number into 2 sig figs? You can either write it as 130 point. Okay, because remember that point will make this 0 significant. Or, probably a better way is 1.30 times 10 to the second liters. Either one is fine. I don't care. Both are acceptable, but that would be your answer for this problem. All right. You can also use the ideal gas law to calculate density. The equation for this is on the back of your periodic table. If you don't have the periodic table in front of you, the equation for density of a gas is taking the pressure times what we would call the molecular weight, which is the same thing as molar mass, divided by the gas constant and then temperature. Now, I'm going to actually show you at the end of this video how we get this, but for right now, let's use this to solve for the problem. So we can calculate the density of a gas as long as we know conditions of temperature and pressure, as well as the molar mass of what gas we're looking at. So calculate the density of carbon dioxide at room temperature, which is 25.0 degrees Celsius, and 1.00 atmospheres of pressure. All right, so I know my pressure. It's 1.00. Okay, the molecular weight, the molar mass. What's the molar mass of carbon dioxide? Well, just for making the video go quicker, the molar mass for CO2 is approximately 44.01 grams per mole. Remember, those are the units for molar mass, grams per mole. The gas constant is 0.08206 atm liter over mole Kelvin. And then your temperature, 25.0 degrees Celsius. We need to convert that into Kelvin, so we're going to add 273.15. That comes out to be 298.2 Kelvin. Notice once again, I round it to 0.2 because of that 1 decimal place. So 298.2 Kelvin would be that answer there. Before we calculate, notice the atmospheres will cancel. Okay, the Kelvin will cancel, the moles will cancel, and then so you'll be left in units of grams over liters. So my answer is going to be in units of grams per liter, which is the units for density. Remember, for gases, we don't do it in grams per milliliter like we did for solids and liquids. We actually just leave it in grams per liter. All right, so all I have to do is just calculate this. Okay, and it looks like with 3 significant figures, my answer should be 1.80 grams per liter. So that's the answer for density. I'm going to end this video talking about actually how we end up getting this. Because you might be like, this is not the ideal gas law. So how did you get this? So I'm going to actually show you where we got this from. If you don't care about that, you can just stop the video right now. We're done. We'll finish up with ideal gas law in the next video. But for those that actually want to know, I'm going to show you real quick how this comes from the ideal gas law. So remember, the ideal gas law is PV equals nRT, right? So there's no density anywhere in this equation, right? We have to do a little finagling. Okay, so thinking about what density is. What is density? Well, density is just a mass over a volume. Right? Well, we have a volume right here, but we don't have a mass anywhere in this problem, right? There's no mass anywhere in here. So, but what's close to mass? What do we have that's close to that? And it's number of moles, right? Because we know there's a connection between moles and mass. So if I did, okay, so here's where I'm going to do a little maneuvering around of things. I'm going to divide both sides by volume here. Okay, so that'll cancel out volume there. And then I'm also, let me do a different color so if I can mix things up a little bit. I'm going to divide both sides by RT as well. So that'll cancel out RT there. And so this hot mess that I just drew right here ends up getting rewritten as moles over volume, okay, that's what was here, is equal to pressure divided by R and T. That was over here. So this is the ideal gas law. We've just moved some things around. All right, so if I were to prescribe units to this fraction right here, what would the units be? Well, N is moles, and volume is in liters. That's close to density, because remember, density is grams per liter, not moles per liter. So how would I get moles per liter into grams per liter? Well, what I could do is I could take this value, this moles per liter, and if I multiplied it by grams over moles, the moles would cancel and I'd end up getting grams per liter. Well, what do we know to be grams per mole? What is that? That's molecular weight or molar mass. So essentially, if I take this value and then also this value, because they're equalities, you have to do the same thing to both sides. If I took those and just multiplied by molecular weight or molar mass, you'd end up converting this value into grams per liter. So like I said, that was a lot, but that's for those that wanted to figure out where that came from. All right, we'll see you in the next video.